Right now, the most advanced telescope ever built is returning data that does not fit the universe. We thought we understood, not because the instruments are malfunctioning, but because the physical laws we have used to describe the cosmos for decades are failing to account for what is actually out there. It was built to see farther back in time than any telescope before it. Every image it captures is not just a picture of space. It is a picture of the past, because light takes time to travel. When you look at something 1 billion light years away, you are seeing what it looked like 1 billion years ago. What the telescope is showing us from those early epochs is deeply inconsistent with the timeline we constructed over a century of careful astronomy. The structures in those early images are too large, too chemically complex, and too organizationally mature. And the problems do not stop at the distant reaches of the universe. Closer to home, in our own galactic neighborhood, planets are doing things that our current models say are physically impossible. This is not a minor gap or a small footnote requiring adjustment. Across 5 separate and completely distinct areas of astrophysics, the James Webb Space Telescope is presenting measurements that challenge the foundational assumptions of our current cosmological model. Let us start at the very beginning, not the beginning of space exploration, but the beginning of time itself, when the universe was born roughly 13.8 billion years ago. It exploded outward from an initial state of incomprehensible density and temperature. In the first few minutes after that event, the fundamental chemistry of everything was locked in. The extreme conditions allowed particles to combine, and by the time things cooled down enough for stable structures to form, the universe contained hydrogen, helium, and trace quantities of lithium. That was it. 3 elements. Nothing more complex existed anywhere. Everything heavier than those 3 elements had to be manufactured later, inside stars. This process is called stellar nucleosynthesis. Stars spend millions to billions of years fusing lighter elements into heavier ones inside their cores. And when those stars die in violent supernova explosions, the newly forged heavy elements get scattered into the surrounding gas clouds. That scattered material eventually collapses to form new stars, new planets, and increasingly complex environments over vast stretches of time. The standard model of cosmology took this chemistry and built a complete timeline from it. In the first few 100 million years after the Big Bang, the universe should have contained nothing more than simple clouds of hydrogen and helium slowly condensing under gravity. Primitive galaxies should have been taking shape, but only barely. Small, irregular, chemically simple. Galaxies like our own Milky Way, with their sophisticated structures and heavy element content, should have required billions of years to assemble. The data coming back from the James Webb Space Telescope does not match this tidy picture. When astronomers directed the telescope toward region of sky known as the Jade's Origins Field, they captured light from an object designated JWST 140. To determine how far away this object is, researchers measured its redshift, which is the degree to which the object's light has been stretched into longer, redder wavelengths by the expansion of the universe. A higher redshift means the object is farther away and therefore older. The redshift measurement for JWST 140 placed it at a distance corresponding to just 300 million years after the Big Bang. At that point in cosmic history, the universe was still in its infancy. Nothing complex should exist yet. The hydrogen and helium clouds were barely beginning to gather under gravity. The first stars were only just beginning to ignite. And yet, the James Webb Space Telescope found something shining brilliantly in that era. Something exceptionally bright, unusually compact, and spanning about 1,600 light-years across. For context, Our own Milky Way stretches roughly 100,000 light-years from edge to edge. Whatever this thing is, it is tiny by galactic standards, but blazingly luminous. If astrophysicists treat this object as a standard early galaxy, its brightness immediately creates a mathematical crisis. In astrophysics, the luminosity of a galaxy is directly tied to its stellar mass. How much it glows tells you roughly how many stars it contains. By that standard calculation, JWST 140 would need to contain a stellar mass equivalent to hundreds of millions of suns. Here is the problem. Accumulating that much stellar mass in only 300 million years is not possible within the framework of current cosmological physics. The process of converting gas into stars is remarkably inefficient even under the best conditions. In the present-day universe, a typical galaxy converts only a tiny fraction of its available gas into stars over enormous timescales. To produce the mass implied by the brightness of JWST, a galaxy would need to convert available gas into stars with something approaching perfect efficiency, and it would need to do it incredibly fast. The physical mechanisms required to force gas clouds to collapse into millions of stars that rapidly simply do not exist in any current cosmological model. Rather than forcing this object into the standard galaxy framework, a team of researchers, including physicist Catherine Fries, used the telescope's near-infrared spectrograph to investigate what else it might be. Spectroscopy works by splitting light into its component wavelengths, producing what is essentially a detailed barcode that reveals the specific chemical elements present and the physical conditions of the emitting source. If JWST 140 were a dense cluster of hot young stars, the spectroscopic readout would show a chaotic mix of overlapping thermal signatures and intense stellar winds. What the instruments returned instead was something strikingly different and highly specific. The most critical piece of data was a sharp, precise drop in the light spectrum located at exactly 1,640 An angstrom is an extremely small unit of length, 1/10,000,000th of a meter, used to describe wavelengths of light. In astrophysics, specific absorption dips at specific wavelengths act as definitive fingerprints. They identify the exact elements that are absorbing light and provide information about the physical state of those elements. The dip at 1,640 angstroms is the unmistakable signature of singly ionized helium, meaning helium atoms that have lost one of their electrons. And critically, the temperature profile around this absorption feature indicates that this helium exists in a cool, diffuse state. Not hot, not compressed, not violently energetic, just a vast, gentle, uniformly distributed cloud. No known configuration of hot fusion-powered stars can produce this exact spectroscopic signature. The object is thermally uniform. The temperature profile is too low. The physical dimensions required to produce this specific light fingerprint point toward something that theoretical physicists proposed years ago but never expected to actually observe in the real universe. A supermassive dark star. A supermassive dark star is not a star in the conventional sense. It does not have a dense, violently compressed core where nuclear fusion is occurring. Instead, it is an enormous, extraordinarily diffuse cloud of pristine hydrogen and helium, puffy, extended, potentially stretching across a diameter larger than our entire solar system. Our solar system spans roughly 8.9 billion kilometers across its outer edge. To describe something even larger than that as a single stellar object is almost beyond comprehension. To understand how such an object could exist, we need to look at the heat source hidden in that 1,640 angstrom spectral dip. Ordinary stars sustain themselves through nuclear fusion. Gravity crushes the core until hydrogen atoms fuse into helium, releasing enormous amounts of energy that push outward and hold the star from collapsing further. The balance between inward gravity and outward fusion pressure is what makes a star stable. When a gas cloud is too puffy and cool to initiate fusion, standard physics says it should keep collapsing until it either ignites or fragments into smaller objects. The spectroscopic data from JWST 140 suggests something else is providing the outward pressure. The theoretical model that perfectly matches the observed light profile involves dark matter annihilation. Dark matter is the name we give to a type of matter that does not emit, absorb, or interact with electromagnetic radiation, meaning we cannot see it directly. We know it exists because of its gravitational effects on ordinary matter. It makes up roughly 27% of the total mass energy content of the universe and acts as an invisible gravitational skeleton holding galaxies together. In the standard cosmological picture, dark matter particles do not interact with each other in any significant way. They are considered essentially collisionless, but theoretical models propose a specific type of dark matter particle called a weakly interacting massive particle, often abbreviated as WIMP. Under extreme density conditions, these particles could collide with each other and annihilate, converting their mass directly into pure thermal energy. The proposal embedded in the data of JWST 140 is this. The object is accumulating dark matter particles into its center. As the density increases, those particles annihilate and release heat. That heat radiates outward into the surrounding hydrogen and helium gas, and the outward pressure from this continuous thermal release is precisely what prevents the cloud from collapsing into a true fusion-powered star. The object becomes what you might imagine as a permanently inflated balloon of gas, held open not by nuclear fire but by the annihilation of invisible particles that the rest of physics cannot even detect directly. A similar fingerprint was found in another object designated JWST, suggesting this is not an isolated reading but a category of object waiting to be formally defined. If supermassive dark stars are real, they completely overturn our understanding of how the first structures in the universe formed. The current timeline assumes that dark matter acted as a passive gravitational scaffold, pulling ordinary gas together from a distance without interfering with the internal physics of what formed. A dark star requires dark matter to be an active, heat-generating agent that intervenes directly in the collapse process, keeping primordial gas hot and diffuse rather than letting it crush down into conventional stars. This would mean there was an early era in cosmic history, predating the first conventional stars, during which dark matter was not just a background presence, but the dominant thermodynamic force shaping what matter could become. An entirely undocumented phase of cosmic evolution. The implications cascade further when you consider the scale problem. A dark star can, in theory, continue pulling in gas and growing indefinitely as long as the dark matter fuel supply at its center remains active. They can reach masses millions of times that of our Sun, objects that massive appearing within the first 300 million years of cosmic history represent a structural formation rate that the current models of mass accumulation simply cannot produce. And yet the data is there. While the mystery of JWST 140 sits in the deepest, accessible reaches of the early universe, a different category of anomaly began appearing scattered across the early universe background fields of the James Webb Space Telescope at slightly more recent epochs, hundreds of them, when researchers first examined the deep field images returned by the telescope. They noticed a recurring pattern scattered across the images corresponding to the era roughly 600 million years after the Big Bang, across multiple image fields. There were small, unusually bright points of light. They were compact and they were red. The astronomical community informally started calling them the little red dots. The red color itself was not surprising. It is a straightforward product of cosmic expansion, which stretches light to longer, redder wavelengths through a process called redshift. But the intensity of that light was the puzzle. Astronomers initially classified them as standard early galaxies. The brightness of a galaxy directly indicates how many stars it contains. For the little red dots to shine as brightly as they did, they would need to be densely packed with an enormous number of mature stars. Running the numbers, these objects appeared to carry a stellar mass roughly equivalent to our own Milky Way. That is a staggering conclusion. Our Milky Way took nearly 14 billion years to accumulate that much mass, finding objects with equivalent mass existing only a few 100 million years after the universe began shattered every accepted model of how galaxies are assembled. Astrophysicists started calling them universe breakers to figure out what was actually happening. Researchers needed more than images. They needed to dissect the light directly. Using the telescope's spectrographs, they collected dozens of hours of targeted observation, data on specific little red dot candidates. When spectroscopy was applied to these objects, the spectrum did not look like the overlapping thermal signatures of billions of individual stars. Instead, the data showed a very specific V-shaped light profile combined with what astronomers classify as broad Bomber emission lines. Bomber lines are spectral features produced specifically by hydrogen gas. The width of these emission lines carries important physical information. When gas is calm and relatively stationary, the emission lines are narrow. When gas is moving violently, the Doppler effect smears those lines out into broader features. The broad Bomber emission lines in the little red dots indicated that hydrogen gas inside these objects was orbiting at speeds exceeding 2 million miles per hour, which works out to approximately 3.2 million kilometers per hour. Normal stars cannot accelerate clouds of gas to those velocities. The only known objects in the universe with gravitational fields powerful enough to drive gas motion at that speed are supermassive black holes. This one measurement changed the interpretation entirely. The little red dots are not massive star-filled galaxies. They are incredibly compact, ultra-dense environments dominated by aggressively feeding supermassive black holes. The intense light is not coming from billions of stars. It is the glare of a black hole consuming surrounding material at a ferocious rate. As matter spirals into the black hole, it compresses and heats up in a region called the accretion disk, generating enormous amounts of radiation. The black hole is surrounded by a thick, dense sphere of cold gas that absorbs and re-emits this energy, causing the entire structure to glow brightly. Researchers began classifying these objects as black hole stars, tiny, extraordinarily dense packages of extreme gravity, wrapped in glowing gas and masquerading as massive galaxies from a distance. This reclassification solves the mass problem of the little red dots, but it immediately creates a different and equally severe problem in the modern universe. Supermassive black holes and their host galaxies do not exist independently of each other. They are bound by a strict mathematical relationship that astrophysicists call the Magorian relationship. This rule dictates that the mass of the central black hole will always be roughly 1/10 of 1% of the total stellar mass of the surrounding galaxy. If the galaxy is large, the black hole is proportionally large. If the galaxy is small, the black hole is proportionally small. They grow together in a locked ratio over billions of years, and this relationship holds across virtually every mature galaxy we can observe in the local universe. Little red dots destroy this relationship completely. When researchers calculated the mass of the black holes hiding inside these compact glowing gas clouds, the numbers did not fit the ratio at all. Instead of being a tiny fraction of the host structure's mass, these early black holes are disproportionately enormous. Some hold roughly 10% of the total mass of their host. Others appear to be nearly equal in mass to the entire surrounding structure. This is a violation of the established rules of cosmic architecture by a factor of 100 to 1000 times. Explaining how a black hole became this immense, this quickly requires confronting a fundamental constraint in physics called the Eddington limit. Black holes grow by pulling in surrounding gas and dust through a process called accretion. As material spirals inward toward the event horizon, it compresses, heats up, and releases intense radiation. This outward-moving radiation exerts pressure on the incoming gas. When a black hole tries to feed too rapidly, the outward radiation pressure exceeds the inward gravitational pull, and the black hole literally pushes its own food supply away. The feeding rate chokes off. Think of pouring water through a funnel faster than the narrow opening allows. Above a certain rate, the system backs up. The Eddington limit is that built-in physical choke point. Because of it, black holes cannot simply grow as fast as they want. They are constrained to a maximum rate of mass accumulation determined by how much radiation pressure their current size generates. Standard models assume the first black holes formed from the collapsed cores of the very first generation of stars. Those early stellar objects might have weighed 10 or 20 times the mass of our Sun. Taking a seed that small and feeding it through a strictly rate-limited process to grow it into a monster weighing millions of solar masses, all within 600 million years, is mathematically inconsistent with the Eddington limit. There simply is not enough time in the cosmic calendar to make the numbers work. Astrophysicists are being pushed toward a completely unverified alternative called direct collapse. In this theoretical process, gigantic clouds of pristine hydrogen gas bypass the star formation stage entirely. Rather than fragmenting into many individual stars, the gas cloud remains cool and unified and crushes directly downward into a massive proto-black hole seed weighing perhaps 100,000 solar masses. Starting from a much more massive seed gives the black hole enough of a head start to potentially reach observed sizes within the available time. Even with this theoretical shortcut, the situation introduces a deeper conceptual puzzle. The Bekenstein-Hawking entropy relation describes black holes in terms of information theory. According to this framework, a black hole's entropy scales with the surface area of its event horizon rather than its volume. This is a deeply counterintuitive result, because in virtually every other physical system, entropy scales with volume. A black hole of a given size contains far more entropy than any other known object of the same physical dimensions. The discovery of black holes that are disproportionately massive relative to their host galaxies raises a pointed question. Could the early universe have temporarily favored the formation of these maximum entropy configurations before assembling the more organized lower entropy structures like conventional galaxies? If so, the conventional picture of cosmic evolution, in which structure builds gradually from small to large, may be reversed or scrambled in the earliest epochs. The little red dots may be telling us that the universe, in its first moments of structural formation, prioritized the creation of the densest, most information-rich objects physically possible before settling into the organized galactic architecture we observe today. Now, let us shift from the extreme early universe to a point that still falls well within the ancient past but is somewhat closer on the cosmic timeline. 800 million years after the Big Bang. And here, a completely different category of impossibility is waiting. Researchers directed the telescope to a specific coordinate in the sky corresponding to a redshift of 6.7, which translates to that 800 million year mark. The initial images revealed a dense, irregular concentration of light. As the research team separated and analyzed the individual light sources, they identified not one galaxy, but 5 distinct galaxies crowded into a remarkably small region of space. The science team named this formation JWST's Quintet. These 5 galaxies are not simply close to each other in the way that distant objects can appear near each other from certain angles. The data confirms they are in direct physical contact. Their individual gravitational fields are completely entangled. The outer boundaries of these galaxies are actively tearing into one another. Billions of tons of matter are being stripped from their standard orbital paths. The 5 systems are merging into a single central structure in real time. To understand the physical mechanics of this collision in detail, researchers utilized a specialized observational mode called an integral field unit. This instrument divides the entire field of view into a microscopic grid of individual positions and captures a complete, independent light spectrum for every single grid square simultaneously. The result is what scientists call a 3-dimensional data cube. It allows researchers to map the exact physical location and velocity of specific chemical elements across the entire collision zone at the same time. The data cube returned a massive, continuous structure of gas, wrapping around all 5 galaxies and forming physical bridges, connecting their individual cores. As the galaxies orbit and crash together, they drag this gas along with them, creating an enormous interconnected web of turbulent material within this gas network. The instruments detected strong, uniform emission signatures from ionized oxygen. The oxygen is not confined to the interiors of the galaxies. The sheer gravitational violence of the merger is actively ejecting it outward, throwing heavy elements into the cold voids separating the individual galactic bodies. The velocity measurements from the Doppler shift of the oxygen emission lines confirmed immense turbulence. The gas is churning and mixing at high speeds as 5 simultaneous gravitational wells pull on it from different directions. The enriched gas cloud spans hundreds of thousands of light years. That is an area significantly larger than our own Milky Way. This observation would be remarkable at any epoch. At 800 million years after the Big Bang, it is physically baffling. Consider the organizational problem first. Gravity operates at a fixed, predictable speed. Drawing massive structures across the expanding void of space takes enormous timescales. Standard cosmological models describe an 800 million year old universe as a sparsely populated landscape containing only isolated, primitive dwarf galaxies slowly feeding on cold streams of undisturbed gas. Finding 5 fully formed galaxies occupying the same tight gravitational space and actively merging is a direct violation of the organizational timeline. Gravity did not have enough time under current physics to drag these massive structures across the expanding void and force them into a synchronized 5-way collision. But the organizational timeline is only the first failure mode here. The chemical composition of that gas cloud is the deeper impossibility. Remember what the Big Bang produced. 3 elements: hydrogen, helium, and a trace of lithium. The early universe contains 0 oxygen. Astrophysics operates on a strict chemical clock for producing anything heavier. To generate oxygen, the universe needs to build and run a factory. That factory is a massive first-generation star. It must form from a cloud of hydrogen, ignite, burn through its fuel over millions of years, begin fusing heavier elements in its core, run out of energy, and die in a supernova explosion. Only the supernova is energetic enough to scatter the newly forged oxygen into surrounding space. This entire life cycle takes millions of years, just for a single generation of massive stars. The JWST data shows massive quantities of oxygen spread across hundreds of thousands of light years of empty space between 5 different galaxies. Getting heavy elements out of the deep gravitational well of a galaxy and into the intergalactic medium requires sustained explosive force. Astrophysicists calculate that this requires thousands of simultaneous supernova firing over hundreds of millions of years to generate winds powerful enough to expel oxygen completely out of a galaxy and into the surrounding void. When you add up the total time required for all of the sequential steps, the arithmetic stops working. You need time for the first massive stars to form, then time for those stars to burn through their fuel and die, then time for their scattered debris to mix with fresh gas and form second-generation stars, then time for that second generation to complete its life cycle and produce outward galactic winds, then time for the winds to carry heavy elements across the gravitational boundaries of the galaxy and into the intergalactic medium. And simultaneously, you need 5 separate galaxies to locate each other, organize gravitationally, and initiate a synchronized merger. 800 million years is dramatically too short for all of those sequential processes to complete. This specific collision is one of the most chemically and structurally advanced structures the James Webb Space Telescope has found in the early universe. It proves that galaxies were capable of enriching themselves with heavy elements and violently clustering into complex multi-body systems at a speed that our current physics cannot easily account for. Now we are going to shift context completely. Instead of looking outward to the edges of the observable universe, let us look inward at our own cosmic backyard, at a world orbiting a star just a few hundred light years away. The star is designated TOI 561. It sits in the constellation Sextans, roughly 280 light years from our solar system. This star is ancient. Its chemical composition shows it to be iron-poor, which places it among the oldest populations of stars in the galaxy, formed during an earlier and less chemically enriched epoch. Estimates put its age at approximately 10 billion years. That is roughly twice the age of our own Sun. Orbiting this ancient star is a super of Earth, exoplanet designated TOI 561b. Its physical parameters are extreme. The planet has a radius roughly 1.4 times that of Earth. It completes a full orbit around its host star in just 10.5 hours. Its orbital distance from the star is less than 1 million miles, or approximately 1.6 million kilometers. To put that in perspective, Mercury, the closest planet to our own Sun, orbits at roughly 36 million miles out. This planet orbits more than 30 times closer to its star than Mercury does to ours. At that proximity, the gravitational mechanics of the star-planet interaction dictate that the planet must be tidally locked. One hemisphere permanently faces the star in constant blazing daylight, while the opposite hemisphere remains in permanent frozen darkness. To investigate the physical nature of this world, researchers used the near-infrared spectrograph aboard the James Webb Space Telescope, locking onto the TOI 561 system for over 37 continuous hours. This extended observation window captured nearly 4 complete orbits of the planet. The observational technique used was secondary eclipse photometry. When the planet passes behind its star from our perspective, only the star's light reaches us. When the planet is visible alongside the star, the combined light from both reaches us. By precisely subtracting the stellar-only readings from the combined readings, researchers obtained a direct thermal measurement of the planet's permanent day side. Standard planetary models predicted a specific thermal signature for this world. A bare, airless rock at this orbital distance would absorb the incoming stellar radiation on its day, side and re-radiate it directly back into space. Based on the planet's size and proximity to the star, this should produce a dayside temperature approaching 4,900 degrees Fahrenheit, or approximately 2,700 degrees Celsius. The rock would essentially glow like a heating element in an oven. The near-infrared spectrograph returned a dayside temperature of approximately 3,200 degrees Fahrenheit, or 1,760 degrees Celsius. That is still hot enough to melt essentially any known solid material, but it is almost 1,700 degrees Fahrenheit cooler than the bare rock. Model requires DOT combined with the cooler than expected temperature. The telescope recorded the complete absence of specific infrared wavelengths from the spectroscopic readout. These missing wavelengths are the critical diagnostic. They provide the fingerprint needed to identify what is physically happening on the planet's surface and in its skies. The only mechanism that can lower the dayside temperature by that amount in a tidally locked world is a thick, volatile-rich atmosphere. A dense gas envelope acts as a thermal insulating layer, absorbing a portion of the incoming radiation and distributing the energy through high-speed winds that carry heat away from the permanently baked dayside and into the permanent nightside. This redistribution of energy is what depresses the peak dayside temperature below what bare rock calculations predict. The telescope did not find a scorched, airless rock. It found a world wrapped in a thick, stable atmosphere, slowly baking on one side, while the other half sits in perpetual cold darkness. And that finding is by the rules of planetary physics. Essentially impossible for a world this old and this close to its star. When a planet orbits directly next to a star, the incoming high-energy radiation heats the gas molecules in the planet's atmosphere. As a gas molecule gains thermal energy, it moves faster. If it reaches escape velocity, meaning the speed required to overcome the planet's gravitational pull, it bleeds off into space. This process is called photoevaporation. A star bombarding a close orbiting world with intense ultraviolet and X-ray radiation is extremely effective at driving this atmospheric erosion. Smaller, less massive planets, lacking the strong gravitational field of gas giants like Jupiter, are especially vulnerable. TO I-561b is a super. It has more mass than our planet, but nowhere near the gravitational anchoring power of a gas giant. Standard atmospheric physics models state clearly that the stellar bombardment at this orbital distance should have blown away all of this planet's gas over billions of years, and this star is 10 billion years old. The planet has endured 10 billion years of constant point-blank radiation from a star that is less than 1 million miles away. The physics are unambiguous. By every established rule of planetary evolution, this world must be a bare scorched rock. Finding a thick, stable atmosphere enveloping it is a direct contradiction of those rules, since the physics are clear that the planet cannot hold on to its original atmosphere over that timescale. The gas envelope JWST detected cannot be the same one the planet formed with. Those original light hydrogen and helium gases were stripped away billions of years ago. What the telescope is detecting must be a secondary atmosphere, one that the planet is actively manufacturing and replenishing in real time. The mechanism capable of regenerating an atmosphere at the required rate is a planetary magma ocean at the orbital distance of TOI 561b. The surface temperature on the star-facing side far exceeds the melting point of any known rock. The entire illuminated hemisphere cannot maintain a solid crust. It is a global ocean of churning, boiling, molten rock. Deep within this magma ocean, volatile elements are dissolved and trapped. As the molten material circulates and rises to the surface, it reaches what you might think of as a planetary boiling point. The magma exhales gases directly into the atmosphere above. Candidates for this gas output include vaporized silicate rock, dense carbon dioxide, and enormous quantities of steam. These heavier, more complex molecules require significantly more energy to reach escape velocity than the original lightweight hydrogen did. This creates a violent, perpetual, self-sustaining cycle of atmospheric destruction and renewal. The star burns away the outermost layer of the atmosphere from above, while the boiling magma ocean below continuously outgases fresh material to replace what was lost. For the atmosphere to remain sufficiently thick to redistribute heat across the planet, the production rate must continuously match or exceed the loss rate. This represents a type of planetary behavior that our models did not account for. A long-term thermodynamic equilibrium existing between a stripping stellar wind and an actively outgassing molten surface. The planet is not a passive object slowly eroding under stellar assault. It is an actively regenerating system running a planetary scale, chemical engine in real time. Finding this kind of complex, active geological behavior on what we would have previously dismissed as an irradiated dead rock tells us that our categories for planetary states are incomplete. Worlds we would have written off as barren may be running dynamic internal processes that we have not yet properly characterized. The fifth major discovery returned by the James Webb Space Telescope brings us even closer to home. Roughly 500 light-years away, a young star designated CT Chamaelantis sits surrounded by a massive swirling cloud of gas and dust known as a protoplanetary disk. The central star is not yet fully mature. It is still in the early stages of its life, actively pulling material from the surrounding disk and settling into its final configuration. Further out within this system orbits a newly formed gas giant, designated CT Chamaelantis b. This planet has already gathered the bulk of its mass, but its gravitational field is still actively pulling in surrounding material. The gas and dust it captures settles into a tight secondary ring directly around the planet itself. Astronomers call this structure a circumplanetary disk. It is the exact environment where moons are assembled to analyze the chemical composition of this system. Researchers used the mid-infrared instrument aboard the James Webb Space Telescope. Mid-infrared observation is the appropriate tool for this type of environment, because shorter wavelengths of light are blocked by the thick dust of a young stellar nursery. Mid-infrared light penetrates that dust barrier. When mid-infrared light hits molecules, it causes them to vibrate at specific frequencies, and each type of molecule vibrates at a uniquely different frequency. These vibrational signatures allow the telescope to conduct a direct chemical inventory of whatever material the light passes through. The scientific team mapped the chemical composition of both the large disk surrounding the primary star and the smaller disk surrounding the gas giant planet. The large stellar disk, which is the primary chemical reservoir feeding the entire system, showed standard building materials when analyzed. Water vapor, basics, standard stuff for a young planetary nursery. What was absent was any measurable trace of carbon molecules. The massive central reservoir feeding the entire system contained no detectable gaseous carbon. When the telescope then targeted the circumplanetary disk orbiting CT Chamaelantis b, the chemical readout was completely different. The smaller planetary disk was heavily saturated with complex carbon chemistry. The spectrographs isolated strong thermal signatures of carbon-based molecules orbiting the planet, and the most prominent detection within this localized disk was benzene. Benzene is not a simple molecule. It is a complex, ring-shaped hydrocarbon. To form benzene, you need a substantial supply of raw carbon. a significant energy source to drive the chemical reactions, and specific physical conditions to allow the ring structure to stabilize. The fact that benzene exists in the circumplanetary disk makes the chemical discrepancy even more striking. Not only does the planetary environment contain carbon while the stellar disk does not, but the planetary environment is actively producing some of the most structurally complex organic molecules we know of. This situation directly violates one of the foundational principles of planetary formation, known as chemical inheritance. The principle works as follows. A star and all the bodies that form around it originate from the same collapsed cloud of interstellar gas and dust. Because they share a single origin point, they share a single initial chemistry. The chemical recipe is locked in from the very beginning. Every planet, moon, and asteroid built within that system is constructed from the same ingredients provided by the host star's disk. The elements in the stellar disk are the only elements available for building everything else in that system. In the CT Chamaelanti system, a young gas giant builds its mass by gravitationally siphoning gas and dust from the primary stellar disk. This is a one-directional supply chain. The planet receives material from the stellar disk, meaning the chemical composition of the circumplanetary disk should perfectly reflect the chemical composition of the stellar disk feeding it. But the JWST data presents a complete breakdown of this supply chain logic. The primary reservoir contains zero measurable gaseous carbon. The secondary pool, actively receiving material from that reservoir, is overflowing with carbon chemistry, including benzene. You cannot extract large quantities of a specific compound from a source that contains none of that compound. The delivery chain makes no chemical sense. To make matters more physically perplexing, the environment directly surrounding a young gas giant is cold and heavily shadowed by the planet itself. The cold temperature and shadowing mean the disk lacks the intense ultraviolet radiation and thermal energy that astrochemists normally consider essential for driving the formation of complex organic molecules. Current astrochemical models cannot explain this environment. A cold, shadowed, localized disk of material should not be capable of manufacturing complex carbon ring structures, especially not while the massive, energetic, radiation-rich stellar disk feeding it contains no carbon whatsoever. The observation forces a rewrite of how localized planetary environments operate. The immediate surroundings of a young gas giant are apparently not just passive collection rings where incoming material settles. They must be active chemical factories. The current hypothesis is that solid carbon locked inside dust pebbles might be arriving from the stellar disk in solid form rather than gaseous form, which is why the stellar disk shows no gaseous carbon signatures. That solid carbon could then be vaporized by localized frictional heating within the circumplanetary disk and rapidly assembled into complex organic structures through mechanisms that astrophysics has not yet fully characterized. If this interpretation is correct, it means young gas giants are not just gravitational vacuum cleaners passively accumulating mass. They are localized chemical engines, transforming and upgrading the raw materials they receive in ways that are completely independent from the broader chemistry of the stellar system around them. That has extraordinary implications for astrobiology. If moons forming around gas giants can accumulate rich carbon chemistry through processes independent of their host star, then the chemical conditions for organic complexity might exist in planetary systems that overall appear to lack the right ingredients. Our understanding of where to look for life-supporting chemistry may need fundamental revision. Taken together, these 5 discoveries share a single striking pattern that cuts across completely different scales of observation and completely different areas of astrophysics At the scale of the very early universe, we have objects forming too quickly, too massively, and with too much chemical complexity for the timeline that standard models allow. At the scale of individual star systems in our own galactic neighborhood, we have planets defying rules of atmospheric retention and moons, accumulating chemistry that the physics of their environment should make impossible in every case. The universe appears to be operating through active, thermodynamically driven processes that are faster, more chemically inventive, and more structurally sophisticated than the frameworks we built to describe them. The standard model of cosmology was constructed over more than a century of observation, using the best available technology at each stage. It is a genuine intellectual achievement. It correctly predicted the cosmic microwave background, the proportions of light elements produced in the Big Bang, the large-scale structure of the universe, and dozens of other phenomena. It is not wrong in the way that a fundamentally broken theory is wrong. It is incomplete in ways that the most powerful telescope ever built is now revealing. What comes next is not simply about fixing the little red dots or explaining where benzene comes from around C. Chameleontis b. It is about something larger. The discoveries coming from the James Webb Space Telescope suggest that the universe is not a slowly unwinding clock. It is not a passive environment in which matter gradually accumulates into more complex forms over uniform timescales. It appears to be a deeply interconnected, thermodynamically creative system that operates through rapid bursts of organization, aggressive chemical transformation, and structural novelty at every scale of observation. Some of the most important work now happening in theoretical physics involves modified gravity frameworks, which ask whether the equations governing gravitational attraction under extreme early universe conditions might behave differently than the equations we have calibrated on nearby galaxies. Other theoretical approaches explore rapid direct collapse models, working out the detailed conditions under which primordial gas clouds could bypass star formation entirely and collapse directly into massive black hole seeds. Still others are probing the interaction properties of dark matter in high-density environments, asking whether the annihilation processes implied by dark star observations are consistent with particle physics experiments here on Earth. The James Webb Space Telescope continues collecting data. Follow-up spectroscopy on JWST 140 and similar objects at comparable redshifts will sharpen the statistical picture of whether the supermassive dark star interpretation holds or whether another explanation emerges. Additional deep field surveys will tell us how common the little red dots actually are, and what their spatial distribution reveals about early cosmic structure. Continued observation of planetary systems like TOI 561 and CT Chameleontis will build a larger sample of chemically anomalous worlds against which theoretical models can be calibrated. The telescope was not built to confirm what we already believed. It was engineered with the specific capability to see far enough back in time and with enough sensitivity to identify exactly the points where our current understanding stops working. It is doing that with remarkable precision. What makes this moment in astronomy genuinely unusual is not simply that we are finding anomalies. Anomalies are a normal part of science. What is unusual is the systematic and multi-scale nature of what is emerging. The failures are not isolated quirks in a single domain. They are appearing in the deep structure of the early universe, in the thermodynamics of close-in exoplanets, and in the chemistry of moon-forming disks around young gas giants. Something about the assumptions underlying our models appears to be missing at a structural level. The researchers working on these questions are not in a panic. They are in the far more productive and exciting state of genuine discovery. The rules are not simply being broken. they are being shown to be incomplete, and the observations now in hand are precise enough to provide real constraints on what the updated rules must look like. What the James Webb Space Telescope is ultimately revealing is that the universe we inhabit is stranger, more active, more thermodynamically creative, and more chemically ambitious than the model we built in the 20th century described. The cosmos is not a background stage on which matter passively accumulates over time. It is a dynamically evolving system that generates structural complexity and chemical novelty continuously, from the scale of molecules forming in the shadow of a young gas giant, all the way to the scale of 5 colliding galaxies, rewriting the chemical history of their entire cosmic neighborhood. We are not at the end of understanding the universe. We are at the beginning of understanding how much more sophisticated our model of the universe needs to become. If questions like these are the kind you find yourself thinking about, then you are exactly the audience that this kind of science is being done for. Consider subscribing to stay connected with new discoveries as they emerge, because the data from this telescope is far from finished revealing what it found. To genuinely appreciate the magnitude of what the James Webb Space Telescope is doing, it helps to understand what came before it and why this particular instrument represents such a qualitative leap in our ability to interrogate the universe. For most of the 20th century, optical astronomy was limited to light in the visible and near-visible spectrum. Telescopes built on mountain peaks or launched into orbit to escape atmospheric distortion gave us images of staggering beauty, but they were fundamentally limited in how far back in time they could see. The expansion of the universe works against the observer here. As the cosmos expands, light traveling toward us from the earliest epochs gets stretched. The further away a source is, the more its light shifts toward longer, redder wavelengths. By the time light from objects that existed only a few 100 million years after the Big Bang reaches us, it has been stretched far out of the visible spectrum and into the infrared. Visible light telescopes simply cannot detect those signals, regardless of how powerful they are. The Hubble Space Telescope, launched in April of 1990, transformed astronomy in ways that are difficult to overstate. The iconic deep-field images from Hubble revealed thousands of galaxies in what appeared to be empty patches of sky, and pushed the boundary of what we could observe to galaxies formed roughly 800 million years after the Big Bang. That was a profound achievement that held for decades. But Hubble was primarily an optical instrument. It could not pierce the infrared veil. It could not see the earliest galaxies. It could not investigate the chemical contents of planetary atmospheres in the detail needed to answer fundamental questions about planetary science. The universe was, in a very literal sense, hiding behind wavelengths of light that Hubble could not collect. The James Webb Space Telescope was specifically designed around that limitation. Its primary mirror is 6.5 meters across, compared to Hubble's 2.4-meter mirror. That size difference translates to roughly 6 times more light-collecting surface area. But more critically, every major instrument on board was optimized for infrared detection. The telescope operates at temperatures close to absolute zero, cooled by a tennis court-sized sunshield to -233 degrees Celsius, or -387 degrees Fahrenheit. At those temperatures, the telescope itself stops generating the infrared heat signatures that would otherwise drown out the faint signals it is trying to detect from the early universe. The combination of large collecting area, infrared optimization, and extreme cold creates an instrument roughly 100 times more powerful than Hubble for the specific purpose of seeing the early universe and analyzing the chemical compositions of faint, distant objects. Nothing like this has ever existed before, and the data it is returning is rewriting textbooks in real time. To appreciate why the timeline violations implied by structures like JWST 140 are so significant. It helps to understand how physicists actually construct a cosmological timeline in the first place. The standard model of cosmology, technically known as lambda CDM, which stands for lambda cold dark matter, is built on the combination of Einstein's general theory of relativity with observational data about the present-day structure of the universe. Lambda refers to the cosmological constant, which Einstein originally introduced and later called his greatest blunder before observational evidence ultimately vindicated it as the mathematical representation of dark energy. The CDM portion describes the dominant form of matter in the universe as cold, meaning slow-moving, and dark, meaning electromagnetically invisible. This framework was assembled over roughly a century of progressive refinement. The discovery of cosmic expansion in the 1920s by Edwin Hubble, the detection of the cosmic microwave background radiation in 1964 by Arno Penzias and Robert Wilson, the measurements of large-scale cosmic structure in the 1980s and 90s, and the stunning 1998 discovery that the expansion of the universe is accelerating, which earned the Nobel Prize in Physics in 2011, all contributed to building what became the lambda CDM model. Within this framework, the history of the universe unfolds in a specific and well-tested sequence. In the first 380,000 years, the universe was too hot for neutral atoms to form. Protons and electrons existed as a plasma. Then the universe cooled enough for electrons to combine with protons into neutral hydrogen in an event called recombination. The cosmic microwave background is a snapshot of the universe at that moment. After recombination, gravity began slowly pulling the distribution of dark matter and ordinary matter into the seeds of the large-scale structure we see today. The first stars, called population 3 stars, formed somewhere between 100 million and 300 million years after the Big Bang. These objects were massive, hot, and shortly, they burned through their hydrogen fuel quickly and died in supernova explosions, seeding the surrounding gas with the first heavy elements. From there, generations of stars formed, lived, and died in a cumulative chemical enrichment process that gradually built up the heavy element content of the universe over billions of years. The first galaxies, assembled over the first few 100 million to a billion years. They started small and irregular, then merged with neighboring structures to eventually build the large spiral and elliptical galaxies we see in the mature universe. This timeline is not arbitrary. It is derived mathematically from the equations of general relativity applied to a universe filled with the observed proportions of dark matter, dark energy, and ordinary matter, the rate at which gravity can assemble structures, the rate at which stars can form and enrich their environments, and the rate at which black holes can grow through accretion are all constrained by the physics built into those equations. What the James Webb Space Telescope is finding is that real objects in the real universe are ahead of schedule in ways the mathematics does not easily accommodate, and it is worth pausing here to make an important distinction. The anomalies being reported are not the product of uncertain or low-quality data. The James Webb Space Telescope is the most precisely engineered astronomical instrument in human history. Its measurements have been validated through multiple independent observational approaches. The spectroscopic signatures identified in objects like JWST 140 were collected using hours of exposure time and analyzed by multiple independent research teams. The little red dots have been confirmed across numerous separate deep field observations. The atmospheric signal from TOI 561b survived rigorous checks for instrumental artifacts. These are not borderline detections riding the edge of noise. They are robust observational findings. The tension between those findings and the standard model is real. One of the most active areas of theoretical development being driven by JWST observations involves the concept of primordial black holes. The idea of primordial black holes dates back to theoretical work in the early 1970s, when physicists Stephen Hawking and Bernard Carr explored the possibility that density fluctuations in the very early universe could have collapsed directly into black holes before any stars or galaxies existed. These would be black holes formed not from the collapse of a star, but from the collapse of a region of space itself in the immediate aftermath of the Big Bang. For decades, primordial black holes remained a theoretical curiosity with limited observational evidence. The JWST data on supermassive black holes in the early universe is giving this hypothesis renewed serious attention. If primordial black holes formed in the first fractions of a second after the Big Bang, they could have had 10 billion years of gradual growth before the early galaxies we are observing with JWST were even assembled. Starting from a massive primordial seed, rather than from a stellar core, might resolve the timeline problem for early supermassive black holes without requiring either the violation of the Eddington limit or the highly specific conditions required for direct collapse. Gravitational wave astronomy is now providing an additional avenue for testing this idea. The LIGO and Virgo detectors and the future space-based LISA mission can potentially identify the mass distribution and merger rates of black hole populations in ways that might distinguish between stellar origin and primordial origin black holes. The intersection of gravitational wave physics and the JW findings is one of the more intellectually exciting crossroads in current astrophysics. The dark matter question opened by the supermassive dark star observation also connects to some of the deepest unresolved problems in fundamental physics. Dark matter has been hypothesized for nearly a century. The Swiss astronomer Fritz Zwicky proposed in the 1930s that the Coma galaxy cluster contained far more mass than its visible stars could account for. Vera Rubin's measurements of galactic rotation curves in the 1970s provided compelling additional evidence. Since then, dark matter has been confirmed through multiple independent observational lines, including gravitational lensing, cosmic structure formation, and the precise acoustic peaks of the cosmic microwave background. What physicists still do not know is what dark matter actually is at the particle level. The leading theoretical candidate for several decades was the WIMP, the weakly interacting massive particle we mentioned earlier. WIMPs were attractive because they naturally produced the right abundance of dark matter in the early universe through a process called thermal freeze-out, and because they were predicted by supersymmetric extensions of the standard model of particle physics. But decades of increasingly sensitive direct detection experiments in underground laboratories have failed to find WIMPs. The Large Hadron Collider at CERN, which searched for supersymmetric partners of known particles, has also come up empty. The WIMP, though still a theoretical possibility, has lost ground. The observation of a potential supermassive dark star does not prove WIMPs exist, but if confirmed, it would provide the first astrophysical evidence that some form of dark matter particle is capable of self-annihilation at high densities, which is exactly the property WIMPs were predicted to have. This would represent an indirect detection of dark matter through its astrophysical effects rather than through a laboratory experiment, and it would narrow the theoretical field considerably. Competing dark matter candidates include ixions, which are extremely light particles originally proposed to solve a problem in quantum chromodynamics. steadily neutrinos, which are heavier non-interacting cousins of the known neutrino particles, and a variety of more exotic proposals, including primordial black holes themselves. Each of these candidates makes different predictions about how dark matter would behave in the extreme density conditions of an early universe gas cloud. The supermassive dark star observations, if they hold up under continued scrutiny, could help rule in or rule out entire classes of dark matter candidates. The implications of the TOI 560 1b discovery extend in a different direction, toward the question of where potentially habitable environments might exist in the galaxy. For decades, the search for potentially Earth-like exoplanets has focused on a concept called the habitable zone, which is the range of orbital distances from a star where liquid water could theoretically exist on a planetary surface. This zone is calculated based on a planet's equilibrium temperature, which assumes the planet receives stellar radiation and radiates it back into space without the complication of significant geological activity or active atmospheric replenishment. The discovery of TOI 561b demonstrates that this simple static model misses important physical dynamics, a world that a simplistic calculation would classify as a dead atmosphere-stripped rock is actually running a complex atmospheric recycling system driven by an active interior. The boundary between environments we consider viable and environments we dismiss as inhospitable is less fixed than our model suggested. This matters for the broader search for biosignatures in exoplanet atmospheres. Current and future space telescopes, including the James Webb Space Telescope itself, are beginning to characterize the atmospheric compositions of exoplanets by analyzing the spectroscopic signatures of starlight filtered through those atmospheres. The assumption underlying much of this work is that an atmosphere, once identified, reflects the planet's formation, history, and long-term environmental conditions in relatively predictable ways. TOI 561b forces us to consider that a planet's detected atmospheric chemistry might instead be a product of active regeneration driven by ongoing geological processes, rather than a passive inheritance from the planet's formation environment. An atmosphere rich in silicon vapor, carbon dioxide, or metal oxides could be the product of a boiling magma ocean rather than the product of surface conditions hospitable to life. This complicates the interpretation of atmospheric detections but also opens up new possibilities. If active geological regeneration can sustain complex atmospheric chemistry under conditions we previously considered too extreme, then the window of geological and chemical activity on rocky planets may be much wider than current models describe. The CT Chameleon system discovery raises related questions about the origin of organic molecules in young planetary systems, and whether the kind of localized chemical factory behavior seen around CT Chameleontis b might have played a role in seeding early planets with the organic building blocks relevant to life. The presence of benzene and other complex hydrocarbons in the circumplanetary disk of a young gas giant raises the possibility that moons forming in that environment could inherit a rich organic chemistry without needing to develop it through slow in situ processes. If a gas giant acts as a local organic chemistry factory, delivering complex molecules into its moon-forming disk, then the moons that subsequently form there arrive preceded with molecular complexity. The outer solar system offers some suggestive context here. The large moons of Jupiter and Saturn, particularly Europa, Ganymede, Enceladus, and Titan, are among the most scientifically compelling targets in the search for habitable environments in our own solar system. Europa is thought to have a subsurface ocean beneath an icy shell. Enceladus actively vents water vapor and organic molecules into space through geysers. Titan has a dense nitrogen-methane atmosphere and surface lakes of liquid hydrocarbons. These environments are richly complex in ways that seem improbable given the cold outer solar system conditions, and the CT Chameleontis observation hints at a mechanism that could explain how that organic complexity was delivered or amplified during the formation of these moons. Understanding how chemical complexity accumulates in the early stages of a planetary system, before planets and moons have even fully formed, is a question with deep implications for how common the prerequisites for life might be across the galaxy. Stepping back to view all of these discoveries together, a few recurring themes emerge that seem to point toward a common underlying gap in our theoretical framework. The first theme is that passive models are systematically failing. Throughout the standard cosmological model, matter is treated as relatively passive. Galaxies form slowly through gradual gravitational accretion. Planets inherit their chemistry passively from their parent disk. Black holes grow at a constrained rate governed by a single balance between gravity and radiation pressure. Atmospheres persist when they are massive enough and erode when they are not. The JWST data, across every scale it probes, reveals instead a universe full of active, self-organizing, thermodynamically creative behavior, dark matter annihilating to power protostars, black holes racing ahead of their host galaxies in mass, planets actively regenerating atmospheres faster than the star can strip them, moon-forming disks functioning as independent organic chemistry. Laboratories. The second theme is that the early universe is far more organized, chemically enriched, and structurally complex than the timeline allows under current physics. This points to either fundamental modifications in our understanding of how fast certain processes can proceed, or to new mechanisms that act as shortcuts through processes we currently model as slow and sequential. The third theme is that scale does not insulate different physical domains from each other. The same dark matter physics that may be operating in the core of a primordial gas cloud has implications for particle physics experiments on Earth. The same thermodynamic principles that determine whether a magma ocean can regenerate an atmosphere are connected to the question of what chemical conditions existed in the early solar system. The universe's physics is coherent across scales, and the failures in our model at one scale tend to point toward failures at others. What does all of this mean for the near future of astronomy? The James Webb Space Telescope has a planned operational lifetime of at least 10 years, with fuel margins that might extend it further. In the time that remains, astronomers plan to push the deep field surveys to even higher redshifts, seeking objects in the first 100 to 200 million years after the Big Bang, a period from which no confirmed structures have yet been detected. If anomalously mature structures exist even earlier than what we have found so far, the challenges to standard cosmology will deepen considerably. At the same time, ground-based observatories, including the extremely large telescope currently under construction in Chile, which will have a primary mirror roughly 39 meters across, will provide complementary observations at optical and near-infrared wavelengths with resolutions impossible from space. The combination of the James Webb Space Telescope's sensitivity and the extremely large telescope's resolving power will allow astronomers to study individual regions within the anomalous early galaxies and directly test whether the star formation rate physics implied by the data is consistent with any known mechanism for the planetary science questions. The next steps involve building larger samples. The TOI 561b detection is one of the clearest atmospheric detections on a close-in super-Earth so far. but it is a single data point. A statistical sample of similar worlds, observed with the same techniques, will reveal whether this regenerative atmospheric behavior is common, rare, or confined to specific stellar ages and compositions. The upcoming Plato mission from the European Space Agency, expected to launch in the late 2020s, will identify thousands of new exoplanet candidates around nearby bright stars, vastly expanding the target pool for follow-up atmospheric characterization. For the CT Chameleontis system, the next scientific priority is understanding the physical mechanism behind the carbon enrichment in the circumplanetary disk. Theoretical modelers are constructing detailed simulations of how solid carbon grains might behave differently from gaseous carbon in the drift and accretion dynamics of a young stellar disk, and how localized heating within a circumplanetary disk might convert that solid material into gaseous and chemically reactive form. Testing these models against observations of additional young systems with similar characteristics will determine whether CT Chameleontis B represents a newly recognized general class of chemical environment or an unusual individual case. What remains, after accounting for all of these specific discoveries and the specific research directions they have opened, is a larger question that cuts through all of modern astrophysics. The universe is about 13.8 billion years old. We inhabit it during a particular epoch, billions of years after the turbulent early period that the James Webb Space Telescope is now revealing. The structures we see around us, from the Milky Way to the planets of our solar system, were assembled during a later, calmer phase in which the extreme dynamism of the early universe had settled into something more gradual and ordered. But the early universe was apparently not what we thought it was. It was faster, more chemically inventive, more structurally complex. That early behavior has consequences for everything that came later. The heavy elements that make up the planets, the rocky surfaces, the organic molecules, the iron in hemoglobin, the calcium in bones. All of this was processed through generations of stars and seeded by the violent early universe that the James Webb Space Telescope is now mapping in unprecedented detail. The James Webb Space Telescope is not just revising our understanding of the distant past, it is forcing a re-examination of the entire chain of cosmic history that produced the conditions for everything that exists today, including the ability to build a telescope and point it at the sky and ask what is out there. That is the scale of what is happening right now in astronomy. We are not adding a chapter to an established story. We are discovering that the first chapter was written in a language we have not yet fully learned to read. There is a historical parallel worth drawing here, because we have been through something like this before, and understanding how that earlier scientific crisis resolved itself offers a useful frame for where we are now at the beginning of the 20th century. Physics was also in a period of confident maturity, followed by abrupt destabilization. By the late 1800s, many physicists believed the fundamental laws of nature were essentially complete. Newtonian mechanics described motion accurately. Maxwell's equations described electromagnetism with remarkable precision. Thermodynamics had established the laws governing heat and energy. The feeling was that physics had reached its endpoint and future work would primarily involve measuring known quantities to greater decimal places. Then several experiments returned results that did not fit the established framework. The photoelectric effect, in which light knocked electrons off metal surfaces in ways that could not be explained by classical wave theory. The discovery that atoms emitted light only at specific, discrete wavelengths, rather than a continuous spectrum. The results of the Michelson-Morley experiment, which found that the speed of light remained constant regardless of the direction of measurement. contradicting the expectation that it should vary depending on Earth's motion through the hypothetical ether medium. These were not minor experimental quirks. They were clean, reproducible, quantitatively precise measurements that directly contradicted the accepted theoretical framework. And the response from the physics community was not to declare the measurements impossible. It was to take them seriously and develop new theoretical structures capable of explaining them. The result was the quantum mechanics revolution and the theory of relativity. These frameworks did not simply patch the old theories. They required completely new conceptual foundations. The idea that energy could only be exchanged in discrete packets called quanta was not an adjustment to classical physics. It was a replacement of one fundamental concept with a completely different one. The idea that space and time are not absolute but relative to the observer was not a correction to Newtonian mechanics. It was a radical reconception of the nature of physical reality. And both of those frameworks, despite how foreign they initially seemed, proved to be profoundly more accurate than what they replaced. Quantum mechanics is the most precisely tested theory in the history of science. General relativity has been confirmed to extraordinary precision through gravitational wave detection, the imaging of black hole shadows, and the behavior of GPS satellites. The destabilization of the late 19th century framework led to something far deeper and more powerful. We may be at an analogous moment now. The James Webb Space Telescope is not delivering anomalies that physicists can explain away with small adjustments. The scale and diversity of the discrepancies suggests something structural is missing. And just as the anomalies of the early 20th century pointed not toward breakdown but toward a deeper underlying order waiting to be discovered, the anomalies accumulating in JWST data may be pointing toward a more complete and more accurate picture of the cosmos. The candidates for what that deeper picture might involve are already being actively explored. Modified theories of gravity are one major avenue. General relativity has been tested exhaustively in the local universe and the solar system, where it performs flawlessly. But the conditions of the early universe, with its extreme densities and temperatures, may push gravitational physics into regimes where the equations that work so well nearby break down or need modification. Various frameworks, including modified Newtonian dynamics and its relativistic extensions, as well as tensor vector scalar theories, propose changes to how gravity behaves at certain scales or in certain regimes. If the gravitational assembly of early structures proceeded faster under a modified gravitational framework than under standard general relativity, some of the timeline problems disappear. Another approach, under serious investigation, involves changes to the assumed initial conditions of the universe. The standard cosmological model assumes that the tiny density fluctuations that seeded the large-scale structure of the universe follow a specific mathematical pattern called a Harrison-Zeldovich spectrum. If the actual initial spectrum was different, perhaps with more power at small scales, the first structures could have formed faster and reached greater complexity earlier than the standard model predicts. The cosmic microwave background measurements from the Planck satellite have constrained this spectrum with high precision, but there is still room for deviations at the very smallest scales, which are the scales relevant for the first galaxy formation. A third avenue involves reconsidering the nature of the dark energy that drives the accelerating expansion of the universe. The cosmological constant lambda in the lambda CDM model treats dark energy as a fixed, unchanging energy density permeating space. But some theoretical frameworks allow dark energy to vary over time, which would change the expansion rate of the universe at different epochs. If the expansion rate in the early universe was slightly different from what lambda CDM predicts, it would alter the available time for structure formation and change the expected timeline. The point is not that any one of these modifications is definitely correct. It is that the JWST observations are providing specific, quantitative data that allows theorists to test these alternatives in ways that were previously impossible. Anomalies without precision are just puzzles. Anomalies with precise measurements are constraints, and constraints drive theoretical progress. The little red dots, for example, are not simply observations of unexpectedly bright early objects. They are objects with measured masses, measured black hole masses, measured gas velocities, measured physical sizes, and measured spectroscopic characteristics. Each of these measurements places specific demands on any theoretical model that tries to explain them. A theory that can explain the mass, but not the gas velocity, or the size but not the spectral shape, has not solved the problem. The precision of JWST data means that candidate theories face a gauntlet of simultaneous constraints, and only frameworks that genuinely capture the underlying physics will pass all of them. This is exactly how science makes progress, not through the comfortable confirmation of expectations, but through the precise characterization of the places where expectations fail. There is something else worth appreciating about this moment, beyond the specific scientific content of any individual discovery. The objects being discussed here, galaxies that formed 800 million years after the Big Bang, a star system 280 light-years away, a young planetary system 500 light-years away. All of these are being observed and chemically characterized using light that traveled to us across distances and timescales that are genuinely difficult to hold in mind. The light from JWST 140 left its source 13.5 billion years ago. The universe itself was only 300 million years old at that point. The hydrogen and helium that made up that object, and the dark matter surrounding it, had not yet been forged into a single generation of stars. That light has been traveling since before the sun existed, before the Earth existed, before life existed. It arrived at the James Webb Space Telescope's mirror and was split into its component wavelengths by instruments designed and built by human beings who understood that a specific dip at 1640 angstroms would tell them something precise about the object's chemical composition, that combination, light that is almost as old as the universe itself, being decoded by instruments designed with exquisite theoretical knowledge, is what makes this moment in astronomical history unusual. We are not just detecting light from the distant past, we are reading it, understanding it, and finding that what it tells us is more complicated and more fascinating than we expected. Science functions as an iterative process of model building and model testing. Every generation of scientists inherits a framework, works within it, extends it, and eventually discovers its boundaries. The generation that receives those boundary findings is tasked with the hardest and most exciting work, building the conceptual architecture that can accommodate both the old successful predictions and the new, confounding observations. The physicists and astronomers working on the JW findings right now are doing that work. They are not in a state of confusion or crisis. They are in a state of productive scientific excitement. They have a telescope that shows them things the previous generation could not see, and they have the theoretical tools to articulate precisely what those observations challenge and what kinds of new frameworks could resolve the tension. What the James Webb Space Telescope ultimately represents, beyond its engineering achievement, beyond its individual discoveries, is the continuation of a project that began when humans first noticed patterns in the night sky and wondered what they meant. The scale of the instruments has changed. The precision of the measurements has changed. The conceptual frameworks have evolved beyond recognition, but the fundamental gesture, pointing instruments at the universe and asking what is out there, and then taking the answer seriously even when it is unexpected, remains exactly the same. The universe appears to be more active, more complex, and more creative than our current framework accounts for. That is not a problem. It is an invitation. Let us close by revisiting each of the 5 discoveries one final time, not to summarize what we have already discussed, but to consider what each one, taken individually, would represent as a standalone finding in astronomy, and what it means that all 5 arrived within the first few years of a single telescope's operation. The discovery of JWST 140, with its spectroscopic fingerprint pointing toward dark matter annihilation as an energy source, would by itself rank as one of the most important observational findings in the history of astrophysics. We have been searching for evidence of dark matter's physical properties for decades. Particle physics experiments have placed increasingly tight constraints on dark matter's interaction cross-section with ordinary matter, steadily ruling out large portions of the theoretical parameter space. The indirect signature being proposed for JWST 140, if confirmed, would be the first observational evidence from the cosmos itself of what dark matter actually does when it is compressed to extreme densities. That alone would generate a paradigm shift in both cosmology and particle physics. The little red dots represent a population-level discovery, not just a single anomalous object. Hundreds of these compact early black hole-dominated systems have been identified across multiple deep-field observations. Their existence as a population with consistent statistical properties, consistent spectroscopic signatures, and consistent violations of the Magorian relationship tells us something deep about how the universe organized itself in its earliest epoch. A single exceptional object might be explainable as an unusual local condition. A population of hundreds of exceptional objects demands a systemic explanation. The little red dots are forcing cosmologists to confront the possibility that the rules governing the coevolution of black holes and their host galaxies simply did not operate in the early universe the way they operate today. The JWST quintet, those 5 colliding galaxies at 800 million years, demonstrates that the universe did not just produce chemically enriched structures early, it produced gravitationally organized groups of such structures. A single early massive galaxy is one thing. 5 of them, in the same small volume of space, deep in each other's gravitational fields, exchanging enriched gas across hundreds of thousands of light years, represent a level of cosmic organization that the Standard Model places firmly in the much later universe. The quintet is not just an anomaly in timing, it is an anomaly in social structure. Galaxies were not supposed to know about each other yet. The atmosphere of TOI 560 1b expands the concept of planetary habitability in a direction we were not looking. Habitability research has historically focused on finding Earth analogues, planets with similar size, similar orbital period, similar stellar environment, similar composition. The discovery of an active, regenerating atmosphere on a tidally locked super-Earth, orbiting an ancient sun-like star in an extreme environment, demonstrates that complex, dynamic, planetary behavior is not restricted to Earth analog conditions. Our definition of what makes a world interesting and potentially complex needs to expand. The benzene in the circumplanetary disk of CT Chamaelantis B raises the deepest question about how organic complexity originates in a young planetary system. One of the central unresolved problems in astrobiology is the origin of the organic molecules that were present on early Earth and may have contributed to the emergence of life. Multiple delivery mechanisms have been proposed, including cometary delivery, asteroid impacts, and in situ synthesis in atmospheric chemistry. the CT Chameleontis observation adds a new possibility. Complex organic molecules might be concentrated and synthesized in the moon-forming disks around giant planets during the earliest phase of a solar system's assembly, potentially delivering a rich chemical inheritance to moons before those moons even finish forming. If this mechanism is common, the distribution of organic chemistry in the early solar system may look very different from what current models assume. The outer solar system, which we tend to think of as the cold, simple, icy periphery of a planetary system, may actually be the zone where the most chemically sophisticated prebiotic environments are assembled. Each of these 5 discoveries would justify extended, dedicated research programs, large international collaborations, and new generations of space and ground-based instruments designed to follow up on the specific questions they raise. All 5 arrived from a single telescope in its first few years of science operations. The James Webb Space Telescope has roughly a decade or more of operational life remaining. Assuming its engineering holds and its fuel reserves last as projected, the scientific community has already submitted thousands of proposals for observation time, competing intensely for access to an instrument that can answer questions no other tool in existence can address. The early years of JWST have been transformative. What follows will likely be more so, as researchers apply what they have learned from the initial anomalies to design observations that directly test the competing theoretical explanations. There is one final thread worth pulling. The James Webb Space Telescope is an extraordinary scientific instrument, but it is also a product of cooperation at a scale that matches the scale of the questions it asks. The telescope was a collaboration between the American Space Agency, NASA, the European Space Agency, and the Canadian Space Agency. It involved engineers and scientists from 17 countries. The development took over 2 decades, surviving budget overruns, schedule delays, and a global pandemic. The telescope includes a sunshield composed of 5 layers of a specialized material called Kapton, coated with aluminum and doped silicon, deployed through a sequence of hundreds of individual mechanical steps in deep space, 360 degrees away from Earth, with no possibility of human repair if anything went wrong. The deployment worked flawlessly. The scientific instruments aboard the telescope are the product of innovations developed across multiple generations of researchers, each building on measurements and theories accumulated over the prior century of astronomy. The spectroscopic techniques that revealed the 1640 angstrom helium signature in JADE's GSC 140R, refinements of methods developed in the 19th century, when astronomers first realized that sunlight passing through a prism revealed specific dark lines corresponding to specific elements in the solar atmosphere. Every observation described in this discussion connects backward through time to an entire chain of prior human inquiry. The existence of the James Webb Space Telescope is itself a product of the same cumulative, collaborative, intergenerational project that produced the scientific framework it is now challenging. Science does not operate through individual flashes of genius in isolation. It operates through the continuous transmission and refinement of knowledge across generations, the building of tools that exceed what the previous generation could achieve, and the willingness to take seriously the findings that contradict what was confidently believed before. What the James Webb Space Telescope is doing is exactly that. It is taking us to the boundary of our current knowledge, showing us what lies beyond it with precision we have never had before, and handing the findings to a generation of researchers who have spent their careers developing the theoretical tools to make sense of what they find. The universe is 4.375 times older than the objects being discussed in the JADE's Origins field discoveries. It has had 13.8 billion years to evolve from the extraordinary and still poorly understood conditions of the Big Bang to the complex present-day cosmos we inhabit. The James Webb Space Telescope is giving us the first detailed look at the earliest chapter of that evolution. And what it is revealing suggests that the first chapter was more turbulent, more creative, and more consequential for everything that followed than we previously understood. The next decade of astronomical discovery will be unlike any before it. The questions are sharper, the tools are more powerful, and the anomalies already in hand are specific enough to point toward real theoretical resolution rather than simply cataloging strangeness. The universe is stranger than our models described it. That is not a setback. It is the most interesting thing that has happened in astronomy in a very long time. There is a specific kind of intellectual discomfort that comes from learning that a framework you trusted is incomplete. It is not the discomfort of being wrong about a single fact. It is the deeper discomfort of realizing that the map you were navigating by does not match the territory, that the things you were confident about were correct as far as they went, but the territory extends in directions the map does not show. That is where astrophysics stands right now, and it is exactly where the science needed to be to make the next leap forward. The discoveries discussed here are not the end point of a story. They are the opening of a new chapter, one in which the James Webb Space Telescope has handed astrophysicists a set of precise, well-characterized anomalies and the challenge of determining what deeper physical reality could produce them. The answers, when they arrive, will almost certainly be more interesting than either the questions or any of our current guesses about what those answers might be. The universe has surprised us before. It will continue to do so. That is what makes it worth watching.